Hi everyone, I'm Daniel here. I'm making a video of how to do post-processing of a GNSS fast static survey here in Trimble Business Center. And just I got a few pictures from the internet before I want to show you this PowerPoint presentation. So for GNSS survey, I call it GNSS because it's commonly called GPS, but GPS is just a US type of GNSS system. So we have in EU the Galileo, and also Russian has GLONASS, and the bigger countries like China has his own as well, but commonly they called the whole system called GNSS, so I stay with this name. We can talk about real-time kinematic or post-processed survey method. The real-time has a correction in real time, which has two way to get. At least I know of two different methods. The one, if you have your own base and you set up your base with a radio transmitter, and you are setting up your base on a known point for the whole day probably, and you set up your radio and you transmit the corrections from the morning till evening, and you can walk with your rover and do your setting out or your survey in real time with your rover. So that's one. Or you can use an RTK network, which nowadays is very popular, especially for us. If we have the Trimble equipment, we have a VRS, virtual reference system network. There are different RTK networks. Well, for VRS is the main thing that they generate a virtual reference point nearby your location. I think it's 4 kilometers or something. Some older receivers can only use a closer base. I think they have a special 2 kilometer virtual reference point if you can choose in broadcast format. But the main theory is that you need a reference point or base point as close as possible to your location, so all the same circumstances around the base as around you, like ionosphere, all the satellite positions, so you receiving signals from the same satellites like the base does, that affect the accuracy. So basically we just using this method, like in surveying we always using this relative survey method, so we have to have a known point and put our base receiver, or even if it's a part of the RTK network, like a national network like we have in Ireland, or every country has his own, we have to have a correction data in some form, and we can receive those. If we use this network, RTK network, we can receive those via internet connection. We can have SIM card in logger or receiver, or we can just connect. We have smartphone today, so we can just make a hotspot. We can connect with our logger to that, and then we can set that internet connection, and just have to log in to the server, and we can receive the stream the data. With VRS, it's actually a correction data will be generated based on the surrounding permanent active control stations. They generate a virtual not existing reference point nearby you, and those correction data will be send to your logger. And that's VRS. When you connect to VRS, that's what happens. Post-processing is, it can be actually two different post-processing. I didn't write it here, but we can do that if we still use the VRS network, just not in real time. So we can just set up our base in the morning on a not known point, like just on anywhere, and just make sure it stays there, not moving. And we can do static measurements with our Rover, which I call it Rover because that's by the system I would call it Rover, but that's actually, it will work like a base, and even the service style in the logger, we use the base template for that. But the basic method is you set up in the morning somewhere on the middle of the site at least for 3-4 hours. It depends on how many reference points around you, like how many kilometers from you, from these RTK networks, from the VRS network. But well, typically 5-6 kilometers the closest, 7, 8, 10 kilometers the next, and you can have, if you're lucky, 3 or 4 active stations around you. For that one, I would leave our base for maybe 2-3 hours definitely, 2 hours definitely at least. And with your second receiver, if you want to go around and do more points, observe more control points, it's really based on how far you are from your middle point, observation. If you are about 1 or 2 kilometers away, like I say, a half an hour would do, definitely, no longer. If you go farther, maybe 40 minutes, 45 minutes. It's basically, I think minimum 20 minutes, plus every kilometer an extra minute. That's what somebody from Correct told me. So that's what they recommend to have. So you can do a day like that. Maybe, of course, you have to physically go to the point, do a setup over the control point. So we can calculate in a day, if it's an 8 hours, let's say 9 hours work, say maybe 7-8 points maximum 8 points we can calculate with that. And then we're going back to the office, and the first thing we will do is calculating or base point on the middle, downloading the RINEX data from the server from the morning 8 hours until evening 6 hours or whenever we finish, and select all the active stations around our base which we want to be involved in the calculation. And we download those RINEX data files, and we just calculate first that point. So after we calculated our base, it will be a known point. The next step is that we can bring in all the rest of the survey data, and relation to our base, which will be fixed. On the same time with the rover, we observe the other control points will be fixed from our base point with a vector. So first there will be a two-step, basically. This post-processing will be done in 2 steps. The first step is from RTK networks points. With a vector we calculate the baseline to the base or base point. We fix its coordinate, and then we just start a new job, and we bring in all the raw data we surveyed. We don't have to worry about, in the next second job, we don't have to worry about the RINEX data anymore, because we fixed, with the RINEX data, we fixed our base coordinate. So we bring in all the points, and we write, or we bring in the fixed. We can export from the first job the fixed base coordinate and just bring in and just bringing in the rover points, or we can bring in everything, select the base point, change the coordinate, make it a control. I will tell you when I'm opening the Trimble Business Center there is a hierarchy system in Trimble Business Center. Basically, you can set the points quality to unknown, survey, map, or control point, and whatever you select to be a control point, that's not gonna move anymore. So we leave everything unknown, and we write the base coordinate in manually or import or whatever way, and then we select it to be a control quality, and then we select all the vectors from our base to the rover points, and then we have the button I will show you in the Trimble Business Center that you can calculate the baseline, just one click. And after, if you're not happy, there are other things you can do. So I'm not going into that now, just wanna show you a few more pictures. Post-processing. Yeah, I think I was talking about this. Again, the Trimble call this fast static. So when you go into the logger and the survey style, you most likely have a fast static. If not, there is a way to do that. You can do your own fast static survey style, which is nothing special. It's working. You have to do some settings on the interval, like how many seconds you want to store the epochs, and where you want the receiver to log in the data. If your receiver has an SD card, you can store everything into the receiver, and before you disconnect from the receiver, you can export and write it on the logger and take out with a USB. Or if you, that's especially useful if you want to leave somewhere a receiver and you have only one logger, and you want to go with your logger and another receiver to do the rover job. So basically, you go in the morning, you start the fast static base survey and start logging. You will see on the receiver a light flashing, and then you can disconnect the Bluetooth and go, and in the settings, Bluetooth settings, you will change the serial number for the rover receiver, and you can connect to that and use another fast static. For rover, for the base fast static, I use every 5 seconds usually to log, to save, and for rover I use every second. So in the whole day measurement on the base, it won't be a huge file if just every 5th second will be stored. So it's a little bit different. When I did for myself, it was a fast static base and fast static rover for me, 2 setting. And then when I go during the day with the rovers, I'm just choosing that one, the fast static rover. And then end of the day, I go back, connect again to the receiver. Sometimes, especially every hour, maybe once, it's worth to go back and see if the battery is still alive, still flashing or something. And then end of the day, you can go back and stop the survey, and then before you disconnect, you can export into the logger and then put into your USB stick, and all your data will be on the USB stick end of the day. The very important thing is that everything will be measured in the same day. So you can't do that. You measure 3 hours on the base and then you shut down and then you do your rover points. Like everything is time specific. It's has to be simultaneous at the same time. Otherwise the vectors, the baselines, they just won't work. The other thing is you have to make sure we don't have to have internet connection good and anything. Usually if you can't use VRS, you use this method to survey, to do some control points, because I don't know why you can't use VRS, because internet connection is bad or other reasons, or it's very weak, you are at the edge of the country or something is not right. Or the other thing is you have to make sure your DOP, geometry DOP, GDOP is quite good, at least under 4, but preferably under 3. It's well, probably is never gonna be 1 or something like that, but 2 point something 3 is alright. And so you have good coverage satellites. And basically that's it. After you did the survey, you just have the data and you go and in the evening into the business Trimble Business Center. Let's see the other page. The RINEX data we need. You can get this data from Trimble's web page vrsnow.ie, and just you have to make sure you do it in 30 days, because after there is no way they will delete, they won't store so much data, so you can just sit on the survey, and you probably after 30 days you should repeat the survey if you didn't download the RINEX data. You can download the RINEX data in 2 minutes, and then after you can do the post-processing next year, doesn't matter, just make sure you have the correct time, the RINEX data for the correct time, even an hour earlier and an hour later, because I'm always confused with this summer and the winter time, so just even add an extra 2 hours. So let's say you went out 9 o'clock, started the survey and finished 3 o'clock, then just download everything from 7 till 5, and then it's a little bit bigger file, but at least you have everything, you will be covered. So RINEX data is basically, you can see on the top picture, I got in this example 3 active reference stations data. I don't call it base because I think it's a reference station with a certificate that it's a good quality station, permanent station, all the time, working 24/7. And I'm using the base for in our case when we go out in the morning, set up our base and put back into the car in the evening. So for the reference stations, I got 3 of them. I think Galway, somewhere in the north. I'm not sure what's the name. Definitely the IEG2. It's Galway. It's definitely. So you can see the coding, how they call them. The first 4 characters refers to the name. The next 3 numbers is the days in the current year, and in this case this survey was made in April, so yes, that's something like that. And the last character is something I didn't write it here. It's basically this survey period. So let's say the file type refers to the year, and different types. The biggest file you see is the observation file, and there is a sample there for the observation file, how it looks like. You can open in a note. It's just a txt file, and you can see different codes there: C1, P1, L1, D1, S1. They the 1 is refers to the L1 frequency, and the 2 is to the L2 frequency. You know, in Geoid we use the dual frequency receivers. So, for example, C1 is the CA code, the distance code. Put it on the L1 frequency. P code is another distance. It's another code using for distance measurement. D1 is a Doppler number. You know, Doppler is basically the satellites are really fast going above, and when they send a signal, even that the signal they send, so we have a closure sometimes, or a negative or positive closure, and when we receive the signal, it's a little bit shifted. Like you imagine the same with the sound waves. When you shout out of the window of a moving car, there is a car coming close to you, it's a higher voice, and then it's going further, it's a lower voice, so it's changing. That's the Doppler number. It needs S number is the signal noise, and the L number is the phase volume in cycles. And from that one, if you see all the code measurements, they are in meter, quite far. But from L1, L2, that's a cycle. It's a phase cycle. You have to multiply that with a number. L1 is a different. L1 has a different phase than L2. I think L1 you have to multiply with something 0.19, and L2 cycle numbers you have to multiply with 0.244 something, and then you can have the difference from those numbers, and then it will give you precision. So basically the software using just these RINEX data files. I don't know exactly how it's calculating. But basically that's it. Yes, and just one more thing for GPS. We calculate everything in a reference system, or reference system is this VGS84 ellipsoid, and then all the satellites has their position. Basically the satellites, how they work, they are on a geosynchron path, and they sending signals with the codes on the signal, and we calculate the distance from the satellites. But the satellites themselves, they don't know where they are, so they their place reference to this ellipsoid determined by ground monitoring stations, and they are near the equator. I think 5 of them in case of GPS system, and they monitoring the satellites position, and they sending up their exact position, and then they are sending this down to the receivers as well. So that's in the RINEX data as well, in the headline probably. So everything is calculated, or all positions first calculated in ellipsoid coordinates x, y, z, and then there is also what we see is most likely the lot long plus the ellipsoid height. So when you bring in a GPS survey and you did not set coordinate system, just you have a GPS survey row, then you have a VGS84 lot long ellipsoid height. After, if you want to use that survey for mapping, or you want to put it into a grid system, well, basically here comes the thing that all the maps are a plane map, so it needs a projection from a 3D object like an ellipsoid to project up to a surface which can be easily made a flat plane. In our case, this is a transverse Mercator projection for old and new ITM system as well. And so the first projection from the ground of the Earth, is everything projected to the reference ellipsoid, and after from there everything projected, that's a second projection, to a plane surface, or a surface can be made plane, like in our case it's a cylinder. Yeah, you will see in the next picture. That's how it looks like. This cylinder is a transfer Mercator projection, and in both cases I think it was in a iRich grid, and the new ITM system has the similar. The only difference, they have two completely different reference ellipsoid. The new ITM systems using the one very close to the VGS84. I think it's almost identical. So this is how it looks like. So after you set the projection, you can you have in the job your global VGS84 lot long coordinates, and you also have your grid. The grid coordinate is the plane, and there is a mathematical projection. Almost every geodetic projection is keeping the angles right. There are some distance and area distortion. The angles is the most important, because in the old days the triangulation was what people used for making the networks, control networks. So this is how it looks like. The other thing we use is the Geoid for GPS. Sorry, GNSS. I swear I will stay with the GNSS, because people like to call it GPS, but it's GNSS. So what we use is the newest, made in 2015. It's a new Geoid 15. Before that was a little bit less accurate Geoid. So basically you can imagine the Earth's surface. You can see on the left picture, that's the green line, and there is a Geoid, a base surface, which is for us is like a datum. It's the Molin head datum. Is some sea level point and an equipotential surface, which every one of its surface point has the same g-force towards the center of the gravity of the Earth, and this goes under our hills and everywhere. So if you would take off the surfaces and you only leave a sea under the ground, and turn off all the moon and everything would affect the sea level change, just leave the the Earth in one system, and as sea level goes through the Malin height, then you have the base surface, and from that surface, well, that's what you get if you go with a traditional level, and because it's always looking towards the Earth's center of gravity. If you take that level and try to level through the country, you pretty much can calculate how far you are from that surface. But with the GPS, it's a different story because you have an ellipsoid height. So you have to calculate, that's a geoid undulation between the geoid and the ellipsoid. And when you survey something on the top of the surface, you have to know that difference, so you will be close to a height you would get if you manually would level from Malin height. Well, it's not gonna be 100%, but the new geoid is quite close, at least on the drawing it looks like. Alright, and the other drawing is pretty much the same. We have the reference ellipsoid, and we have the geoid, and you can see the orthometric height. You will see actually these heights in Trimble Business Center, the small h, the big h, orthometric height. So at least you can go back to this picture and maybe have a better understanding. That's it. So now we open Trimble Business Center. And I'm using an old job here. Have to find that. So first I just make a new job, new project, a blank one. You see, I will show you. Okay, every blank template, if you go to the project settings and you go to the coordinate system, there is no coordinate system group zone, but the global is always VGS 84. No geoid model, nothing, so that just gives the lat long and ellipsoid height probably. But I need to set here, or you have to do as well. It's you can set here for baseline processing. That's what we're going to do in fast static post-processing. You can set some tolerance if you want, but I'm happy with that for now. What I wanted to do with the units coordinates, I want to have more precision for lat long, a little bit more. Okay. The next thing, I show you the survey file. So this is an old job. So this is how the RINEX data looks like. We don't need the txt file, just the 9 RINEX file. And this is the job itself. So in our case, it was an easy day, only 6 points. This was the probably 4 hours, 4 or 5 hours observed point, and we calculate first this one. you can see with a big T, it's a bigger letter, it's different. And it's also the size. You see the size, it's only every 5th second was stored, but and these ones, they're all 1 second stored in these ones, but you see it's almost double the size. So still, if it would be 5 times bigger if I record every 1 second. So I just bring it in now. If you're not sure when you did the survey, there is a good way to check here. That's the start. It's 2019, the 15th of March, and this is the end time. So it's about less than 4 hours. Yeah, 3 hours 40 minutes. So it's selected. That's all right. You don't tick this one. That's something. It's a service. I think you can send to someone who can post-process this one and send it back to us. We can do it ourselves. That's an antenna information. Or you can, if you want, you can change height here. You see what type of antenna we used, file name, some information of receiver. That's it. We just bring it in. That's fine. The very important thing, we click on the point and you check that it's not control point, not brought in as control point. You see the grid coordinates is 0 because there is no coordinate system set here, so just only the global coordinates important. These are the VGS84, lot long, and ellipsoid height, and they're all unknown. This is the unknown. If you're not sure this is it, then you go here and you change. You can see it. You see it's unknown, and the elevation is unknown too. Okay, so the next thing, we bring in the RINEX data, all the points. I show you one way to do it. You can go to the VRS now.ie and download all these RINEX files in a zip, and then you extract, and then you just select them like this and you bring them in. I will do that later. I just want to show you something. There is a free you have to have an account to log into that vrsnow.ie for these RINEX files, but there is a free way to do it. If you go to survey and then internet download, you can see a couple of things. Well, first of all, the precise orbit information sometimes coming later, so even if they transmitted the orbit parameters up to the satellite and we received it via the receiver, sometimes it's changing. They fine-tuning this, and then after a couple of days you can download a precise orbit, final one. I try. Ready to import. Yeah, it's here. Okay. Well, it's definitely ready because it's been a year. But if you did this yesterday, you might not okay with this final orbit. You can go to the rapid. Still, it's only a millimeter or two. Maybe it doesn't make a big difference in my opinion. So what you can do here, you go to the internet download configuration, you can make a new site and select from a list, and you see the closest. If you sort them out by distance, then you see the closest stations, so you can select for in this case it's Castlebar, 24 kilometer. It's a quiet distance. These are free, so we have much more option in the VRSnow.ie, and I think if I can select, probably I would go for the hours, not the days, and this one, maybe these two, and then you can bring them in, so you don't have to download, but probably it's the best way to download, so I will just do this one. And then you bring in. Take some time. Yes, you see the 3 points. I'm looking for the names. I will see them somewhere else probably. So this is Galway, definitely. These another two active reference station. So you select it all and you go to OK, and it's brought in. You see this is 5 kilometers, so these are 20, 26 and something like 50 kilometers. I close this one. So what I have to do now, these 3 points, they are the permanent active reference stations, part of the actual VRS RTK network. So they're 100% sure that they are there. So I'm selecting them, and with this icon here I make sure these stays where they are. So this will be the hierarchy. We will calculate the position, exact position of our base point, the middle, using these 3 points with the baseline from them. So go to this one as well. This one as well. Okay, we don't have to use this one, this one, this one. We can disable those baselines because they're not gonna fix anything here anyway. You see they got a different color now. What we have to calculate, these 3 baselines basically. So just to imagine what's happening here. The same period of the time the measurement was carried out. So this baseline knows that 2 end of the baseline there is 2 point with 2 observations. Each observation, well, it basically this is 4 hours, this is maybe more, but it's only on the shortest time is the determining this calculation. So what's happening in this time? During this time there was a measurement on this point, and because this is a known point, let's say this was measured somewhere here, a meter, 2 meters northeast, and then also difference in height as well. So the system knows at that time, because of some ionospheric disturbance or something, error in clock error or something, this position was placed here instead of here. So this using this vector to fixing the positions of this point wherever it was observed on the same time, it knows that it can't be there, so it most likely somewhere here, or opposite, if it's here it has to be somewhere here, because if it's measured this point here, then most likely this measurement in real is somewhere here. So that's basically, you can imagine this thing. And the same thing from here and the same thing from here. And these three baselines will well, basically one would be enough, because we have three, we will have error, so we can share the error, weight the error, and we can at the end do an network adjustment as well and have a error ellipse. We will see it later. So select the baseline you're interested in and go to process baseline. Okay, everywhere fixed. There is no huge error, so we can save it. Okay, so they now all done. If you were not happy with the result, let's say from this point was let's say the baseline. This, if we were not happy with this one, from this point was a bigger error than from those two, you can go to session editor here in the same survey tab. Okay, and you see that this 3 hours 40 minutes period from this left to the right, this is all I think this GPS, and this is the Russian, the R GLONASS satellites, and see if somewhere the L1, L2, I try to explain how it works. So if you have two dual frequency, you can eliminate some errors and you can have a higher precision. Like that's how we achieve the centimeter accuracy with the phase measurements, not only code on the L1. So this is, one of them is L1, the other is L2, two different frequency, and sometimes they're not 100%. So with selecting these areas just with the left click, you can disable these parts. You can make it more clear. There is plenty of satellites, so it won't be missed. And then you can process again. Oh, sorry. It won't be a huge difference, it was quite okay anyway. You see almost nothing, so just save it, doesn't matter. Once you're done here, you can have a network adjustment. This is the two-dimensional a lot long, and this is ellipsoid height, and we make the fixed coordinates for the 3 control point. We're not going to the weights yet. We do first the adjustment, and we see if it's failed. We can do some adjustment on the vectors, but this is successful, so you don't have to. You can go here and change these values if it's failed and do until it's successful, but this is alright. So that's an adjusted network now. We can close or OK. First we can save this. We don't actually need to save. If you want, you can save it for later. The main thing is that this point now is correct. So if you see the global coordinates, and you see I just added the decimals, so it's an accurate one now. You can export this point with global, and then you can bring into an ITM and you have a grid. Or we can actually just change now, because there is no coordinate system set yet, it's a global. We can add a coordinate system now, and then we can have an ITM coordinate for this point. Let's do that. If you go to units coordinates, sorry, let's see, in units, no, in coordinate system, then you go to the change, and then we select ITM. Let's see what's the options here. Yes, that's the one, ITM, that's what we need. The Geoid model is the 2015. And keep adjustment. Now it's shifted to the right place. You see the coordinates already telling us that it's somewhere north. So now you go to the point, and now you see the grid coordinates are here. The globals are the same, nothing's changed, and check the local ones. That's what I was going to say earlier. The ITM is using the GRS80 ellipsoid, which is very similar to the VGS84. I think the long axis is 100% the same. Just the other smaller axis a bit smaller, I think. You see these coordinates VGS84 and these GRS80 ellipsoid, local ellipsoid, and that's the cylinder, the ITM Irish Transfer Mercator projection, the grid coordinates. Just compare the two ellipsoid coordinates, they're pretty much the same. If you see, north got a very little, maybe it's even less than a millimeter probably. So when we coming to, that's why the new ITM coordinate system is it's GPS friendly. It's basically the GRS80 ellipsoid is in a good relation to the VGS84. It's almost the same. You see the geoid was added, so ellipsoid height, this is elevation from the geoid. So if you compare the two, you see how much the geoid above the reference ellipsoid. That's just something you can see on these coordinates. You can write this on a piece of paper, or you can select the point and export it here, whatever. If you can export it like east-north elevation and code, point number east-north elevation code, then it will export these grid coordinates, which is alright, because next step we can start with a job with ITM, or you can export it with a global point latitude, longitude, ellipsoid height as well. Well, just easier probably in this one, or you can just really, what I used to do, just write this on a piece of paper. I have so many files, sometimes it's just an extra file, but only a few. You can write this on a piece of paper really. So what we do next, what I do is actually I'm taking a photo of this. Yeah, that's another thing. At least you will have global coordinates as well on the same. Okay. So close. What we can do before you can save this job and come back, or you can, before we close this, you can save this baseline processing report and also point derivation report. You can save this one. It shows you the tree vector and the adjustments and everything. It's quite okay. The confidence level. So that's something you can print out to the client. The other thing, if you go up here on the top row in the reports, there's a baseline processing report. So this is how it looks like. You see it's passed, that's the most important thing. 3 baseline, all passed. You can print it out or save it here. I don't save this. So the next thing is next. If we open again, open a new project, and if you have an ITM template, you choose it. No, it's just quite empty software now. I just installed a couple of weeks ago. I still should have this template somewhere, but I just set up the coordinate systems quicker for now. So you can go save the project, test. Go to project settings, coordinate system, you can go to change, and you can select from the list. Geoid model is right, projection is right, and maybe changing the units. Alright, and save it. So when everything is right, we don't need the RINEX now, just all our survey. Okay. If you still want to change something here because you realize something was measured wrong or something not correct, or you can even change the method. You know, you want to measure to the bottom of the antenna, center of bumper. It's cool. You can do that here. Just go OK now. So yes, this was a road, so it's not so nice, but I picked it as a middle point. That was all day, or that's 4 hours long there, and all the rest of the points were just 40 minutes basically. So what we do now, we come here and change the coordinate on this one. See the picture? One 068 358.043 elevation 27,095, and make sure this is control quality because we already calculated this one. Okay, and it's changed. And now with the control holds you can select all the baselines, and now we can calculate on the survey process baseline. Yes, this is the result. All fixed, all correct. Save. You see they're all because there is only one correction, there is no point to do adjust network here. There is nothing to adjust. It's only one. There is one measurement or one correction from one point, one baseline to each. Also, if you're not happy with something, the same thing, you can go to session editor and you see the same things here. You can change it and recalculate it. So since we were happy, go to the points with the control, select all of them and point derivation report. That's one thing we will need. you see from this the vector was calculated, fixed precision we achieved, these kind of things. Okay, and the other thing is we need basically what I need for traverse adjustments. Next step, these will be my control points when I'm adjusting the so here it what is happening from all year long measured reference points. We selected them control quality and determined the middle point, and then when it was calculated, selected that middle point for a control quality fixed point and calculated the baselines. We were observing them like almost for an hour, and then for next step these will be control points, these baselines, and everything we traversed with the total station, those will be calculated, but these will be then all control quality. So that's the hierarchy, that's how we go. And then the final after the traverse adjustments, all our control points will be fixed and all the surveyed points will be also adjusted. So what I need here is a point list. So also right click here. Yes, so this is our fast static result, final result. That's what we really need here. You can print out or anything. That's it for now, I think. Next time I show you how to, if you have a drawing, how to change between the two coordinate system, the Irish grid and the ITM. Well, something I show you now something here, and then after that's it. So once you select the points, you go to export, and then you export them in a global point latitude, longitude, ellipsoid height code in global. Then you basically just here you select a folder where you want, you name it, and you export it. That's gonna be a CSV file. Next time, if this was in Irish grid, for example, the global coordinates are global coordinates. They're VGS84. They're not the Irish grid ellipsoid, not local ellipsoid. So if you export a global lat long, doesn't matter what coordinate system you have set, this always go back to the first ellipsoid, the global VGS84. So with the Trimble Business Center, that's the best way I figured out to do. If you select this one, export, make sure you have the accuracy, the decimals on precision is long enough, and then when you bring it in, you open a next job, obviously ITM, and you bring in the CSV file, you just pull it in, and you select from the list. Well, let's do it, just why not. I just select and let's do in this one, test one, save, export. Okay, so this now is ITM. So we do backwards. We transform this from ITM and we will make an Irish grid drawing. So let's close this one. You can save it or not, doesn't matter. It's here. If you see, it's slat long, basically ellipsoid height. There was no code, but there would be a code anyway. What you do now, open again. Make a new project. Change the coordinate system to that's transfer Mercator 75 Irish grid with the Geoid model 2015. Well, this one I couldn't find in Civil 3D. It's interesting, they only have the 65. I think there was a map adjustment with this old Irish grid system in 75, and there is a few 100 mil or some different, not even 100 mil, probably 50 mil, some small different some areas. So when I do transformation with Civil 3D, I'm using the 65, which is a slightly bit different. So this is it now. You see the coordinates is just generally smaller numbers. So I bring in this one. And important thing is that you select the right, this one, point ID, lot long, ellipsoid height, global, definitely global. Import, I think, or next, yeah. And it brought in. If you see now this point, I think that was the base. You can see now that there is a big difference, definitely in longitude. If you see, but latitude as well. The global ellipsoid polar coordinates are still the same, but the local it's so the local ellipsoid is the IRI modified ellipsoid is completely different. I think it's a smaller one, just it's best fit on under Ireland, but it's not a geo-centered ellipsoid. And you can see that it's completely different here. And also the grid, it's still a transverse, it's a cylinder projection, but the false center is on somewhere else. So you can, if you just look at the coordinates, you can say it's not ITM, it's different numbers. So that's how you can do that. If you can have thousands point, doesn't matter. Well, I don't know how to do the lines. I suppose if we have a code, then you can do like a survey and line work after using the codes. But with the points, there was a way to export them with the global coordinates and then brought them in, and then transform or using these common coordinates between the two systems to determine the grid coordinates. So that was one way using Trimble Business Center. And next time I will show you how to do complete drawings, DWGs in AutoCAD. How to transfer between coordinate systems if you receive Irish grid map with grid coordinates, and how to make it ITM without actually moving anything or manually transfer or shift or scale or rotate. So I think that's it for now. Thank you for your attention, and see you next time. Bye.